Hello kids, we're going to talk about strong acids versus weak acids today. Acids are substances that surround us in everyday life. The use of acids range from providing essential nutrients for our bodies to dissolving metals. Some acids are safe to handle with bare hands or even in food preparation. Other acids will severely burn human skin. It's important to understand how these substances can be acids and yet have different properties. Okay? So if we look at the first picture, we have water molecules in a solution, and we are adding a solution that has a hydrogen atom bonded to some cation. And when they're mixed together, you'll notice the water molecules are now H3O instead of H2O because they have picked up that hydrogen. Remember, the definition of an acid is a proton donator, which is a hydrogen atom, hydrogen nucleus. Proton donator, hydrogen nucleus, same thing. And so the acid over here has donated his hydrogen to each one of those water molecules. We can also see that the anion now is free to swim about in the water. Okay? And we have 100% of the acid ions have interacted with water. If we look at the second one, now we've got a few reactions. We had two water molecules that picked up a hydrogen, and then there's two ions, but the rest are still the same. Okay? First question. What do each of these symbols mean? Well, this guy is obviously water. The second picture is obviously the acid molecule because we can read our key. The third picture is that hydronium ion, H3O, with a positive charge. And the fourth picture is that conjugate base piece that we've talked about earlier. If you've already done the definition of acids and bases worksheet, that is. All right. What product do the solutions have in common? Well, the products are the hydronium ion and the anion, which we'll call X with a negative charge. Use a complete sentence to explain the formation of the product in part A from acid molecule and water molecule. Well, if you have acid plus water, you end up with hydronium plus the anion, or conjugate base, if you will. Assume that solutions of hydrochloric acid and hydrogen fluoride, hydrofluoric acid, are similar to those in Model 1 are prepared, and infinitesimally small samples are collected and analyzed to determine the amount of ionization. Based on the data, calculate the percent ionization for each acid solution. All right, well, if we look back here, percent, is part of a whole. How many of our water molecules reacted? For this first one, we had 100% react. For the second picture, we have 2 out of 10 reacting for 20%. All right. So for a 0.06 molar hydrochloric acid, if we start with 40 molecules, it tells us that 40 molecules have reacted, 40 out of 40, 100%. All right, for B, the hydrofluoric acid, we know from counting just now that 20% are going to react or ionize. So if we've got 40 to begin with, 10 out of 10 react here, right? So we know, and 2 out of 10 react here, so we can just multiply those by 4. 2 times 4 would be 8 out of 40, so we would have 8 reactions. If we have fewer acid molecules, so it's less concentrated, hydrochloric acid is still going to react at a rate of 100%. The hydrofluoric acid is still going to react at a rate of 20%, which is going to be 4 out of 20. Electrolytes are substances that dissolve in water to produce ions in solution. We talked about this when we did the lab with the different substances, and we put them on foil and heated them to see which one melted fastest, and we tried to dissolve them in water. And the ones that dissolve in water would then conduct electricity, and that is the definition of an electrolyte, something that conducts electricity in water. And that's what this next definition says. The presence of ions allows a solution to conduct an electrical current. Ions may be produced because the substance that dissolves is ionic, or because the substance reacts with the water to produce ions. The more ions that are formed in solution, the stronger the electrolyte. Non-electrolytes are substances whose aqueous solutions do not contain ions and therefore do not conduct an electrical current. So, which of these is the better conductor? Okay, how can you tell? Well, do you remember what we did in the lab? We used my little homemade conductors, and we put the two ends of a wire in, and we had a light up. Well, notice we've got two lights here. We've got this light and this light. Who has a brighter light based on the drawing? Well, the first one does, that ionizes 100%. Okay, which solution is a better conductor? Well, the first one, which was the strong acid. The bulb is brighter. However you want to write it. Number 5, describe the relationship between ionization of acid and conductivity. The higher the ionization, the higher the conductivity. The conductivity of the solution and strength of the electrolyte. Again, conductivity, the greater the conductivity, I should have used greater in the other one, means a stronger electrolyte. All right. Consider conductivity data in Model 1 and the ionization data in Question 3. Ionization data in Question 3. A strong acid, is hydrochloric acid a strong acid or weak acid? It is a strong acid because it has 100% ionization. Hydrofluoric acid would be a weak acid because it's less than 100%. Does a change in concentration affect the strength? Looking back at number 3, the concentration changed, but it does not affect the percent ionization. How about if I spell that correctly? No. Ionization. One of the reactions, there's a single arrow, the other is a double. Now, there's a typo on your page. There is only one arrow in both of them. So with the second one, the weak acid, please put a second arrow pointing back the other direction. The symbols imply how the reaction occurs. In the first one, 100% if it's 100% ionization, then the reaction's going to occur all the way to 100%. But the second one is going to be able to go back and forth at that 20% level. There's still some left to ionize, but at the same time, there are going to be some that unionize. So the extent to the way a reaction occurs, this means that the reaction is complete. And this means that the reaction, I want to say hang on. It's in equilibrium, which is what I wanted to say. Equilibrium means it's, the reaction is proceeding towards the products and then going in reverse towards the reactants at an equal rate. What does it mean about the strength of the acid? Well, if the reaction is complete, it's strong. If the reaction is in equilibrium or incomplete, it's weak. A student states a solution of 4 molar sulfuric acid is stronger than a 1 molar sulfuric acid. Construct a well thought out response to this. Well, while a 4 molar is more concentrated, both will ionize completely. Therefore, both are strong acids. As opposed to talking about concentration and strength. All right, in the beaker below, draw a representation to show 10 molecules of a weak acid dissolved with 20% ionization. All right, so we need 10 weak acids. Here's our weak acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And then we'll need, it says only include water molecules that react. So if it's a 20%, 2 of these guys are going to react. All right, so we need 2 water molecules. We're going to take this guy and break him apart. And we'll take this guy and break him apart. Okay, and we've got 20% of them reacted. You have conductivity meters in 1 molar solution of nitric acid, nitrous acid, and acetic acid. Why was this guy named nitrous? Because that's nitric, or nitrite. Nitrite becomes us. All right, the 1 molar, here I'm going to write these out as we go. We've got nitric, nitrous, and acetic, because that is acetate. So this guy is giving off a lot of light. This guy is giving off some light. And this guy is very dim. So who's the strongest? Well, obviously the most light is going to be the most ionized, and the least light will be the least ionized. Write a balanced chemical equation for HNO3, HNO2 reacting with water as they are mixed in an aqueous solution. All right, nitric acid plus water will completely ionize because it's the brightest, and I happen to know it's one of the strong acids, and you'll know that shortly. The nitrous acid is not as strong, so we will have the double arrow. Just like that. All right, what are our strong acids? Well, there are 6 of them. Hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid. These are the 6 strong acids. When you get to AP, Rice has a sheet that works really well for solubility charts, and this is one of the key components, is the 6 strong acids. All right. There you go.